Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 10th, 2025, and we're diving into a fascinating ICLR conference paper published just a few months ago on January 22nd titled Cheating Automatic LLM Benchmarks, Null Models Achieve High Win Rates. This paper explores a really interesting problem, how easy it might be to trick the systems we use to test how good large language models, or LLMs, are. These tests, often called LLM benchmarks, increasingly use other LLMs as automatic judges or auto-annotators to score performance. The researchers investigate whether even very simple, non-informative models, which they call null models, can be designed to fool these auto-annotators and achieve surprisingly high scores, potentially undermining the reliability of these benchmarks. Okay, so this first figure really illustrates how these null models can try to fool the evaluation systems. Part A shows the auto-annotators template for Alpaca Eval 2.0. That's the standard format the automatic judge uses to see the instruction and model outputs. Then, Part B displays some, quote, persuasive responses. These are pretty basic attempts to cheat, and they achieve very low scores, specifically low length-controlled win rates, or LC win rates, which is a metric that adjusts for response length to ensure fair comparisons. But then Part C reveals their structured cheating responses. These are much craftier, designed to confuse the judge, and they get remarkably high length-controlled win rates, showing how effectively they can game the system. Building on those structured cheating responses, this next figure from page 4 actually shows an example of how such a response is constructed. We're looking at a user message, essentially the input given to the automatic judge. It cleverly includes an instruction to ignore the above model outputs, and then presents a new, likely much simpler set of outputs. This whole setup is designed to confuse the auto-annotator's syntactic analysis. That's basically how the system breaks down and understands the structure of the text, leading it to incorrectly favor the cheating model. Alright, so this table on page 6 really drives home the point. It summarizes their main results, comparing their cheating methods against what are called state-of-the-art models. Basically, the best models currently available. We see scores for Alpaca Eval 2.0, Arena Hard Auto, and MT Bench. Their structured plus RS method, which uses that clever structured response combined with random search, a technique where they try many random options to find the most effective cheating prefix, consistently gets top scores. For instance, it hits an 86.5% length-controlled win rate on Alpaca Eval 2.0, smashing the verified state-of-the-art's 57.5%. This really shows how vulnerable these benchmarks are. Alright, so these plots on page 9 really dig into how the optimization process boosts the cheat's success. We're looking at performance across different llama models as more optimization steps. Essentially, more refinement using that random search are applied. For the null model, the length-controlled win rate starts low, but then skyrockets with more steps, pushing past 90%. And even when an informative model like GPT 3.5, which already has a decent start, is paired with the cheat, its win rate is also driven to over 90%. This really shows the robustness of the optimized cheating approach. Building on that robustness, this table, also from page 9, further explores the cheat's effectiveness, this time when llama models, specifically the Llama 3 Instruct family, act as the auto-annotators or automatic judges. We see that the simple structured cheat initially struggles against these llama models. For instance, with Llama 3.8b Instruct as the judge, it scores a very low 2.9% length-controlled win rate. But once that random search optimization is applied, the structured plus random search method sees its length-controlled win rate soar to an impressive 95.4%. This really underscores the power of the optimization across different judging systems. Okay, so to really put their best cheating method into perspective, this table on page 30 details win rates for different attack strategies on the Alpaca Eval 2.0 benchmark, where GPT-4 is the automatic judge. We can see that other baseline attack methods, they score practically zero. The author's own structured responses get progressively better, but it's their structured plus random search that really shines. It achieves an impressive 86.5% length-controlled win rate, surpassing even the verified state-of-the-art model's 57.5%, which clearly demonstrates the severe vulnerability of this benchmark. So given how effective their cheating methods are, the researchers also tested some defenses. This table on page 30 shows the structured cheats win rates against these defenses on Alpaca Eval 2.0 with GPT-4 as the judge. A defense called PPL window, which measures text perplexity, or how unusual the text is, had no effect. Self-reminder, likely an instruction for the judge to be more cautious, did lower the cheat success. And smooth LLM, a technique that modifies responses to be more robust, almost completely stopped the cheat, though this approach might also hurt normal responses, making it less practical. So while some defenses show a little promise, the overall picture is quite stark. The key takeaway here is that even null models, which are essentially AI systems designed to output a fixed, often irrelevant response, can be manipulated to achieve top scores on these automatic benchmarks. These benchmarks often rely on other large language models as auto-annotators or automatic judges. This vulnerability really highlights the urgent need for more robust evaluation methods. Thanks for tuning in to the AI Research Roundup.